Welcome back. Our next topic is Bayesian Additive Regression trees. Also known, how do you say that, Trevor?
BART.
I just want to make fun of your accent. It's BART.
That's what I said.
BART. Okay. So we're going to discuss Bayesian Additive Regression trees, or BART, an ensemble method that uses decision trees as its building blocks. Now, we've talked about 2 or 3 other methods already for using decision trees in supervised learning. Bagging and random forest, for example, make predictions from an average of regression trees. Each one is built up using a random sample of data. So we either sample the data as a bootstrap sample or we sample the features, right? And each one's built up separately and they're averaged at the end. Boosting, on the other hand, uses a weighted sum of trees, each of which is constructed from fitting a tree to the residual of the current fit. So that they're not built independently, but they're built in sequence, right? So each tree tries to capture the signal that's not yet accounted for by the current set of trees. So it's kind of a forward stage-wise method.
So Rob, what does BART do differently?
Well, if you wait for the next slide, you'll find out. Okay, BART is related both to random forest and boosting. It has the random feature as in bagging and random forest, that it draws random samples to build trees. But it also has a similarity to boosting in that it uses the other trees and kind of a parser residual to choose the next tree to improve the overall fit, to try to account for the signal that's not been captured by the current model. So it's got similarities to both random forest, bagging, and boosting. The main novelty, as you'll see, is the way in which the new trees are generated, which is quite different than the other methods. It can be applied to regression, classification, other problems like survival analysis, but here we'll just focus on regression. Okay, so first of all, in a picture, this is the idea, and then we'll go into details in the coming slides. A number of trees that are fit in parallel. So one chooses a number k, maybe a few hundred, and b steps in each stage, and each tree is changed b times as the algorithm proceeds. For each tree, say the first tree, we start with the root node, right? So they all start with the root node, and then perturbations are applied to the trees to change them. These perturbations, as we'll see, can be of various kinds. We can add a branch, or we can delete a branch, or we can change the predicted values at each of the nodes. In this case, since we started with the root node, each of these trees gets a single split added to them, although the split points and split variables are different. And then at the next stage, this tree, we've added another branch on the left. This tree, we've actually removed the existing branch, and it's back to the root node. And this tree, again, we add another branch on the left side. And this continues for maybe a few thousand steps, these perturbations, to get a whole sequence of trees of varying sizes with different predictions in the root nodes.
So Robert, it looks like, the iterations, where you go 1 through B,
yep.
And it seems like what you're doing is maintaining K trees at each step.
Exactly.
And each step you change each of those K trees in some kind of random way.
Exactly.
Yeah.
So at the end, we make our final prediction by averaging the prediction over all K sequences of trees and all steps B. Okay, so let's actually go over that now in more detail with some notation. So the number of regression trees, that was the different columns in that previous picture, is K, and the number of iterations for which we apply the algorithm we'll call B. Okay, and the prediction at a query point X for the Kth tree in the Bth iteration we'll call F hat sup B sub K. So at the end of each iteration, we have K trees, and our prediction at the Bth step is simply the sum of those predictions. Okay, so what do those iterations look like? At the beginning, as we saw in the picture, each tree starts with a single root node, and the prediction in each tree is just the average of the overall observations. So our overall prediction at the first step is simply this average.
So we divide each of them by those averages by K, so that when we sum up K of them, we get the overall mean of Y.
Exactly. And then in coming iterations, 2, 3, etc., this is what happens. We take the parser residual for all tree but the Kth tree, we subtract off the current fit, and we form what's called the parser residual. And then we build our tree on the parser residual. But we might think, well, I'll just build a regression tree directly, but from scratch. But instead, what BART does is it takes the existing tree at that step and it perturbs it in a certain way. Okay, and so instead of fitting a fresh tree, it chooses a perturbation of the existing tree from the previous step for the kth tree from a set of possible perturbations, trying to improve the fit. Now we're trying to make the sum of squares on the partial residual as small as possible. And there's two different ways this perturbation can be made. We can change the structure of the tree by adding or pruning branches. Right? And we saw that in that picture. In one case, we added branches. In another case, we actually removed the only branch. Or we can leave the tree alone and change the predicted value at each terminal node. Okay? So we choose among a set of perturbations to vary the tree. And what we're doing here is sort of moving around the tree space, right? In this kind of in a similar way, bagging and boosting do the same way. They generate a set of trees that tries to cover the set of sort of possible trees. This is also moving around the tree space, the space of possible trees, but in a different way, through perturbations. Here's some examples. Suppose we start, we're at a step where we have for the kth tree, we have at step b minus 1, this tree. One possibility for perturbation is to leave the structure of the tree the same, right? But the predictions in the terminal nodes are varied a little bit, right? Like this 0.4079 is changed to 0.444221, etc. Another possibility is to remove a branch. Well, here it actually looks like we've trimmed off this branch here. So we've removed these three terminal nodes, right? And then here's another possibility. So instead of trimming a branch, we've added
quite a bit of randomness in this trimming, Rob.
Yes.
Similar to your mouse work on the computer.
I wish I had a mouse, but I don't. So, okay. So in this fourth example, I've added a branch, looks like here, right? So it can remove branches, add branches, or change the predicted values in the nodes. So what do you get from all this? We get a collection of prediction models, right? At each step B, again, our prediction is the sum of the predictions for the K trees. And as I mentioned, the prediction is the average of all the predictions for all trees and for all B. Except that since this is a process which is random and it starts in a place and it kind of, you hope it's going to settle down after a while, what's done is a kind of burn-in. So you don't actually, the first L iterations you actually throw away. So maybe B is 1,000, L is 100. That means you ignore the first 100 steps in the prediction and you take the average of the remaining 900.
So Rob, what I'm seeing here is that for any given B,
Yeah.
the BART prediction is like a boosting model, right? It's a sum of trees,
Right.
K trees.
Right.
But the difference here is that you got many of those, and you've created these many by having this randomization in the tree selection each time.
That's right. And another difference is you're not building each tree by a simple tree fit to the residual. You're actually taking the existing tree and doing a perturbation. So it's actually kind of slower too, right? You're not fitting as hard to data each time. And I think we'll see in the example of this section that that overfitting is reduced by this kind of the slower learning. Another nice thing about BART is not only do you get, as we'll see, quite good predictions, you get other quantities like quantiles, right? So for example, you can take the percentiles of the non-Burnian predictions as a measure of uncertainty of the final prediction, right? You get not just one number, but a collection of predictions. So if you want, say, that the 95th percentile of the prediction, you can use the 95th percentile of the predictions after burn-in. Here's an example on the heart data, which we saw in the book, in which we applied, in the first edition, we applied bagging and boosting in random forest, and now we're going to see what happens when you apply BART. So the number of trees here was 200, and the number of iterations, the B was brought up to 10,000, right? And the burn-in here is 100, you can see. Here's the training and test error for boosting, which you've seen before. That's the dark blue and the dark green. The BART training error is in gold, and the BART test error is in light blue. And you can see the training error goes down more slowly than in boosting. Again, this is the evidence that it's not fitting nearly as hard. But the test error is competitive with boosting. There it is.
So that's really interesting, because you can see boosting, it really, as you fit more and more trees, really starts to overfit.
Right.
The training error keeps on going down, and the test error starts increasing.
Right.
BART is showing behavior more like random forest, where once you reach a certain number of trees, it just flattens off, and it doesn't seem to overfit.
Right, it's not as aggressive, which is one of the selling points. As we say, it'll work well out of the box. You don't need to tune it very much because it's not as prone to overfitting as, say, boosting is. So where do these perturbations come from? Are they just sort of pulled out of the air? Well, it turns out it's a Bayesian method, hence the name Bayesian Additive Regression trees. And we didn't talk much in the book about Bayesian methods. We talked a little bit about Bayes' rule and Bayes' methods, but the Bayesian method starts with a prior on the parameters. You collect the data, you have a sampling model. You then combine the prior and the sampling model to get a posterior distribution. Well, it turns out that the perturbations in BART correspond to a certain prior distribution on the parameters. The parameters here being the split points and the values at the terminal nodes. So we won't go into detail here, but it's a Bayesian method under a certain prior. And what we're doing with these perturbations is actually drawing from the posterior distribution from that model. Furthermore, the BART algorithm can be viewed as a Markov chain Monte Carlo, or MCMC method, for fitting the BART model. MCMC is a standard way of drawing from a posterior distribution from a Bayesian model. So the point is that this method, which may seem kind of ad hoc, is actually, it's grounded in statistical theory. It's a real posterior distribution from an actual prior distribution. And we typically choose values for B and K that are large, and the burn-in's pretty moderate. So, for example, reasonable choices might be 200 sets of trees, 1,000 iterations, or we did 10,000 of that example, and a burn-in of about 100. And as I mentioned, the selling point of BART is that it works well right out of the box without much tuning, which we saw also with random forests and bagging.